So one other way of finding the moment of inertia, we have this table, which comes in handy. You will once in a while see problems that have what I mentioned before, the point mass. We use the hoop equation. So this cylindrical hoop or ring, same idea, because the mass is all concentrated out at that distance r, we use mr squared. Now, capital R is just the way they have labeled it in this picture, in this table. We can write it as lowercase r, but we just need to know r, as far as these objects in the picture are concerned, means the radius of the object. In a point mass, we mean the distance the very small object is from the rotation axis. And I'll point it out when we get to problems that have a point mass and when we're going to treat something like a point mass. Now, the one other situation in terms of calculating moment of inertia is called the parallel axis theorem. Now, it is named such because it applies for any object that is rotating around an axis. So, for example, on this cylinder, if the axis is parallel to the one in the picture, to the one that goes through the center, but it doesn't go through the center, this would be our new axis. Since this specific rotation axis is not one of the ones in the picture, we need a way to be able to calculate for it. The equation looks like this. I new, meaning around this new axis that does not go through the center, can be calculated by taking the I for the center, ICM, center of mass. So I for the object that passes through the center of mass, the rotation axis does, plus md squared. M is the total mass of the object. D, coming back to the diagram, is the distance. D is this distance between the original rotational axis in the picture that goes through the center and where this new axis is located. So for example, let's say this new axis was halfway. So we have a disk with new axis halfway between the center of mass and the outer edge. So to use this equation, I hope it's somewhat obvious, the new axis must be parallel to the one that goes through the center. Okay, so if we have a new axis that isn't parallel to that axis in the picture, then we cannot use this equation. So this new axis I've drawn, the I new in this case, we would take the 1/2 mr squared the table gives us, because that is I, when the disk rotates around that axis that goes through its center of mass, plus m is the total mass. D, in this case, I shifted the axis to be halfway between the center and the outer edge. So that would be half of the radius. So I have to square that. So 1/2 mr squared plus 1/4 mr squared, because I have to square the 1/2 as well as the r. Let's see, this would be 3/4 mr squared. Would be I around this axis that is parallel to the one in the table, but halfway out to the outer edge. It's bigger, 3/4 mr squared versus the original 1/2 mr squared. It's bigger because on average, the mass is a bit further from the rotation axis, which makes it a bit harder to affect the rotation. Let's say we have our axis on the outer edge. So still the cylinder, but let's make our new axis out here along the outer edge. And it could be on any point of the outer edge. So I could have drawn it over here. So I knew 2. Our second I knew. Same equation, so I would still want 1/2 mr squared for the I through the center of mass. The difference here is that from the center all the way to the outer edge, we have shifted this a distance of r. So D is bigger now. This new axis is farther from the center. So we would actually end up with 3/2 mr squared if this disk was rotating around its outer edge. So this is applicable to any of these objects. We could talk about a spherical shell around its outer edge. The difference would be the I center of mass part, because we would need to use the value for the spherical shell specifically, and then account for that D, the distance we have shifted the axis. Now, one last thing, this thin rod about the end is actually the solution to the parallel axis theorem. If we didn't have thin rod about its end, we just had the thin rod about its center, and we wanted to find it around its end, I'm only showing you this to show the practice in the parallel axis theorem. I mean, we can obviously grab the equation right here because it's in the table. Oh, that's messy. All right, I knew, meaning I around the end. I center of mass, I have to grab the 1/12 ml squared because I need the I through the center specifically. And then I would add the shift from the center to all the way to the end, which would be 1/2 the total length of the rod. So 1/12 ml squared plus, when I square that, I get 1/4 ml squared. Let's see, common denominator, 4/12 ml squared. That is where the 1/3 ml squared comes from. So again, we can use that result. That's not a problem. But we can very well have a problem that asks us to find I around, ooh, that one's not very parallel. Let me try that again. I around halfway. So for the rod, we're changing it to halfway to the end. I knew we still need the I for the center of mass, so the 1/12 ml squared, plus m d squared. D is this distance, we've shifted it. So that wouldn't be half of L, that's 1/2 of 1/2 of L, right? So that, we mean we've only shifted it 1/4 of the way down from the center. So 1/12 ml squared plus 1/16 ml squared. Let's see, 48, that would be 4, 48, that would be 3, so 7/48 ml squared would be the moment of inertia around that axis. So how the mass is distributed around the rotation axis is absolutely crucial in determining this I value This I value, called moment of inertia, is essentially replaces our m. So to oppose rotation, or to be able to cause rotation, relating that back to a net torque, this rotational inertia or moment of inertia is an important piece of determining the angular acceleration, the rate at which your object, whatever object happens to be rotating, the rate at which it's going to rotate given the torque acting on it. So a cylinder is not necessarily going to have the same angular acceleration. I changes based on where the axis is. So we have to take that into account when we're relating the net torque to the motion. But again, our main ways of finding moment of inertia: 1, I is equal to mr squared for a point mass. Again, a point mass, we just mean the mass itself is very small compared to how far away it is from the rotation axis. So like the Earth orbiting the sun, the Earth, comparing the Earth's size to the distance from the center of the sun, Earth is rather small. We could consider the Earth in that one specific situation to be a point mass. If I was sitting on a chair that could rotate and I was holding an additional mass in my hand, and I'm holding it away with my arm outwards, I could treat that as a point mass because it would be small compared to the length of my arm. Outside of a point mass, this table as a whole comes into play. Again, the table itself is in the test notes, but not with the pictures. So make sure you are familiar with these pictures to go along with the object and axis. And then the third way is this parallel axis theorem. If we look at the table and the axis is not in the right place, oftentimes we will need to use the parallel axis theorem to calculate I.